Okay, welcome to this week's homework review video. I'm going to try recording this at a lower resolution, so if you guys notice any differences, that's why. But I think you'll still be able to tell what's going on, and we can save some file storage space while we're in the process. Alright, so this week's homework wasn't a whole lot of new material relative to the one that was just due on Wednesday. There's a lot of conceptual problems, a lot of trends and things we want to understand. So not a whole lot of mathematical computations this time, but a lot of things we have to understand and really know sort of in and out to be able to predict some of these trends and answer a lot of these types of questions, which are often true or false type questions and things of that sort. So let's go through. I again picked the problems that we performed the worst on. Most of these we had a success rate of less than 50%, so we're going to try to clear up some things with this video. Alright, so the first couple had to do with Subshell Energies, and this was one that I got a few questions on during the week, and we overall had a little bit of trouble with. So we're doing comparisons between Subshell Energies for 3 different situations. So we're trying to find which of these comparisons is incorrect, and as we always do, more stable means it has more negative energy. So we're trying to compare the stability of subshells in different atoms and ions, and making predictions about those. So there's basically 3 things we have to know to answer this question that have to deal with subshell energies, and each of the 3 points concerns one of those. So the first point A is the 1s orbital in hydrogen is more stable than the 1s orbital in He+. Now when we're dealing with one electron species like hydrogen or ions like He+ that also only have one electron, we immediately want to think about the Boar equation, because that very accurately tells us the energy of the subshells. And the important point about the Boar equation, well, there's a few important points. One is that the form of the equation looks like this. It's the Boar constant. So this minus 2.18 times 10 to the minus 18 joules. We have a z squared term. So z is the number of protons in the nucleus, so that affects things, and then it's going to be 1 over n squared. Now, the important point for this question is the difference in Z between hydrogen and helium, but another important thing that we'll get to later is that the Bohr equation only depends on n. It only depends on the first quantum number. So the fact that we're telling you it's a 1s orbital, doesn't really mean a whole lot in this case, because any orbital in the first shell, which has to be a 1s orbital, but any of those would have the same energy. We'll get to that later, but for now keep in mind that there's a difference in the number of protons, so as Z increases, the energy becomes more negative. So this first one, the 1s orbital in hydrogen is more stable than the 1s orbital in helium, is not correct. Okay, because helium has more protons in the nucleus. There's a stronger attraction to electrons that are in the 1s orbital, and that makes the subshell more stable. So whenever you're comparing one electron species, you look at the value of Z. Now if we go on to the other ones and try to figure out, why are these ones true? So here for choice B, we're comparing the 2s orbital in helium is less stable than the 2s orbital in helium plus. So now we're comparing the same atom but with one fewer electron in the second case. So for this one, we don't have a set of equations that's going to easily tell us this, because helium as a neutral atom, has 2 electrons. So the Bohr equation doesn't apply to 2 electron species. We don't have another equation that we can easily use to decide these things, but what we have to realize is that when we're removing electrons from a subshell, we're going to make it more stable because we reduce the electron-electron repulsions. So this is going to be more stable, He+, more stable because we have less electron-electron repulsion, or in this case, no electron-electron repulsion because there's only one electron left. So when you're comparing the same atom, as you remove electrons, the subshells become more stable because you reduce electron-electron repulsion. Okay, so that's how we want to think about it in this case. And then finally, the last one, we're talking about the 2s subshell in lithium is more stable than the 2p subshell in lithium. So this is where, if we have a multi-electron atom, it's the value of n and L determine energy. Okay, so we have to think about both the first and the second quantum number. So both of these determine the energy of our subshell, and that's where we get the ordering that we have from the periodic table that tells us which subshells get filled first. Alright, so that's, we have in a given shell, for a given value of n, we have S is lower in energy than P, lower in energy than D, lower in energy than F. And that's what we're asking you here, 2s versus 2p. The 2s will always get filled first, it's more stable. So this is true for multi-electron atoms. We do have to remember for one electron atoms or ions, it only depends on n. So that's the difference between one electron species and multi-electron species. So choice A is the one that is incorrect. That's the answer we would have wanted to pick. We had a fairly wide distribution of other answer choices that people chose. Many of you especially thought that choice B would be incorrect also, but remember, as we remove electrons, we make the subshell more stable because we're reducing electron-electron repulsions. All right, so that was a conceptual one, and then another one that was conceptual about subshell energies. Again, we're looking for the one that's not a true statement, so let's go through these one by one. All right, in high-numbered shells of multi-electron atoms, some subshells of different shell... Okay. All right, this is worded poorly. That's part of the problem. Sorry about that. In high-numbered shells of a multi-electron atom, some subshells of different shells have nearly identical energies. So what we're asking here is, if we're comparing, for example, 4s and 3d, this is the classic example. I know the wording on this one is confusing, so I apologize. But if we're comparing 4s versus 3d, they have different shell numbers and different subshell numbers. Is it possible that they're close in energy? And the answer to this is yes. So we know that 4s fills before 3d, and they're very close in energy, which is why we have some of those exceptions to the Aufbau principle, where the 4s and 3d can both be partially filled, which is not a normal situation. So some subshells, especially if we go higher and higher in value of n, so the 4s and 3d are a classic example, or if we have the 6s and the 4f and the 5d, all those can be very close in energy, even though they're in different shells, but they have different subshell numbers, so that affects things as well. Okay, choice B. In the hydrogen atom, all subshells of a given shell have the same energy, and this is true. Alright, so this is true. We're looking for the false statement. Choice B is true, because as we talked about in the last slide, if you're talking about one electron species, the Boar equation tells us that only the value of n, only the shell number, determines the energy. C. In a multi-electron atom, the various subshells of a given shell have different energies. This is also true, and this is, as we talked about in the last slide, why we have S is lower in energy than P, lower in energy than D, lower in energy than F. When you have multi-electron atoms, you have shielding and penetration that come into play as well, in addition to just the basic subshell energies, and that's why these different subshells have different energies. Okay, in choice D, orbital energies are usually different in multi-electron atoms than the corresponding ones in hydrogen atom. Okay, this is also true, again, because in multi-electron atoms, we're adding protons to the nucleus, first of all, and we're adding in electron-electron repulsions, so both of those are going to affect the orbital energy, and they're likely to be different from those of hydrogen. And then finally, choice E, the orbitals within a subshell of a multi-electron atom have different energies. So here we have to know the definition of shell, subshell, and orbital. So what we have to remember is that if we're given a value of n, which is the first quantum number, that's our shell number. Okay, and that, as we talked about, in one electron atoms, this determines the energy. And then in multi-electron atoms, if we have n and l, that's the subshell, and that's going to determine the energy for multi-electron atoms. And if we have individual orbitals, that's a value of n, l, and m sub l together. Remember that the value of m sub l has no bearing on energy. So what this means is that in a given subshell, all the orbitals have the same energy. So for example, if we have the 3p subshell, we have 3 individual orbitals in this subshell, and all 3 of those have the same energy. So this one's going to be false. So within a subshell, all of the orbitals in that subshell have the same energy. In an S subshell, there's going to be 1 orbital, so obviously that has no other orbitals with it, but in a P subshell, you have 3 orbitals, all of them with the same energy. The D subshell has 5 orbitals, all with the same energy, and F has 7, and so on. Alright, so within a subshell, we want to be aware that all orbitals have the same energy. Okay, so this is the answer we would have wanted to pick for this one. This is the incorrect statement. Finally, one more question about subshells, which again has to do with their energies and also some rules about quantum numbers. So we're again looking for the false statement. All the following are true except. So we have 5 choices here. We have to find the false one. And so the first one, A, the n equals 3 shell has no F subshell. Alright, so remember that if we're talking about S, P, D, and F, those tell us the second value of the quantum number L. So for S, P, D, and F, we have L is equal to 0, 1, 2, and 3. So for an F subshell, L equals 3, And remember that if n equals 3, the maximum value of L is n minus 1, which can be 2. So we cannot have a 3f subshell. So this is false. Wait, sorry. Yeah, this one's true. Sorry. The n equals 3 shell has no f subshell. That's going to be true because in the n equals 3 we have s, p, and d, but no f because L cannot be 3. Alright, B, there are 3 p orbitals in every shell of an atom except the n equals 1 shell. This is the one that a lot of you picked. Alright, now it's true that if we have a p subshell, there are 3 orbitals. We just talked about that in the last question. P subshell has 3 orbitals. However, this gets back to the definition in the rules for quantum numbers again. If we have an n equals 1 shell, that means the only value of L is 0. So when n equals 1, we can only have a 1s subshell. That's the only subshell in n equals 1. So we can't have a 1p, which means there are no p orbitals when n equals 1. If there were p orbitals, there would be 3 of them, but it's just not, that's not a allowed value for that quantum number. Okay, choice C, all s orbitals have spherical shapes. Most of us got that one. Each d subshell has 5 d orbitals. We mostly got that one. And then the one that many of us also picked, choice E, the energies of subshell and the shells of a hydrogen atom vary as s, p, d, etc. So for choice E, this is again where for 1 electron atoms, the energy only depends on n. So when we're in hydrogen or those other special ions like helium plus or lithium 2 plus, all we need to know for the energy value is n. That comes from the Boar equation. So in a hydrogen atom, s, p, and d all have the same energy within a given shell. All right, so this one is going to be false. All right, so choice E is the one we wanted to pick. Basically, there is an equal split between choice B and choice E, if I remember correctly. So many of us picked choice B, but remember we can't have p orbitals in n equals 1. And for choice E, it only depends on the value of n. All right, so we want to get those things right. These are conceptual questions. It's really about knowing the concepts in and out. Being able to approach them from different angles and answer questions about them. All right, so definitely review those topics if you're having trouble. All right, the last couple deal with periodic trends and electron configuration. So let's go through these as well. Atomic ionic radius. Which of the following has the smallest radius? We're given phosphorus, Cl-, aluminum, S2-, and gallium. All right, now this is not the simplest of the atomic radius problems because here we don't have any real relationship between these features. They're not isoelectronics. They have different numbers of electrons. So it's going to be the comparison is not as straightforward as some of the other ones that we've seen. Now, if we're looking at these answer choices, phosphorus, Cl-, aluminum, S2-. So those first 4, these are all in the n equals 3 part of the periodic table, the third row of the periodic table, and they all have 3p valence electrons. So we would expect all of these to be fairly similar. Remember, when we're adding electrons to the same subshell, that tends to give things that have similar radius. Gallium is on the next row of the periodic table. It's below aluminum. So here we're filling a 4p orbital. So when you go out to a completely higher subshell like this, 3p versus 4p, we would expect this to be the largest. We're filling a whole other orbital. So we can eliminate choice E because it's nowhere near the others in the periodic table, at least in terms of being on the same row, which is the important part for determining radius. But between these 4, we have, we're expecting them to be similar. We want to know which one is largest, which one is the smallest. All right, so the periodic trend, remember, is typically is left to right if we're talking about, neutral atoms. If we're talking about neutral atoms, the radius decreases as we go left to right. So these are all in the same row, so we're considering that trend. And that would be true if these are all neutral atoms. We have some that are anions. So the problem with this is, what happens when you're talking about an anion versus a neutral atom. And what the point this question is trying to make is that when you add extra electrons, the radius goes up by a lot. So whenever things are close, these are all close to each other in the same row of the periodic table, anions have much larger radius. So if you're comparing a neutral atom and an anion where they have the same types of valence electrons, in this case 3s and 3p valence electrons, the anions are going to have a much larger radius. So if we're looking for the smallest radius, we can eliminate Cl- and S2- because those are anionic species. And when you add electrons into these outer shells, remember we're going to increase the electron repulsion, and that has a very large effect on the radius. So if we look at, if you have your textbook, section 212 talks about atomic radius. So if you look at the figure 233, which is on page 89 in the version of the book that I have, it lists atomic radius. And as a representative example, if you look at Cl, that has an atomic radius of 99 picometers. We talked about that one in class. Now if we go to chapter 3 where we start talking about ionic radius, that's going to be in, I believe, section 3.3 if I'm not mistaken. So it would be nice if they put these things right next to each other, but they're in different sections of the book. But if we go to 3.3, where it talks about ionic radius, if we compare Cl to Cl-, so Cl, neutral, is 99 picometers, and then the ionic radiuses are given on table, or figure 3.5, which is on page 111 in the version of the book that I have. And if we look at Cl-, that has a radius of 181 picometers. So adding electrons to the outer shell has a huge effect on the radius. In this case, it almost doubles it. So when you're comparing a neutral to an anion, the anion is always going to be bigger if they're in the same row of the periodic table. So that's one we want to keep in mind for this one. So all we're left with is phosphorus versus aluminum, and remember that the radius decreases as we go left to right. Phosphorus is to the right of aluminum, so phosphorus is going to be the smallest one. So choice A is what we wanted to pick for this one. All right, so this is a little bit of a complicated problem, but hopefully, this is not something I mentioned explicitly in class, but we can be aware now that anions have much larger radii than the neutral atoms that are comparable to them. All right, so if we go to the next question, electron configuration and group number, we're given a partial ground state electron configuration, and we want to determine the full configuration as well as the atom that it corresponds to. Now, if in this question there were a couple answers that were almost correct that a lot of us picked, and we just want to understand why they weren't completely correct. Because here we're comparing three things. We have the full electron configuration, the atomic symbol, and the group number. Now, if we look at the picture we're given, it has 2s and 2p subshells that are, and the 2s is fully filled and the 2p is partially filled. So this is a valid picture that follows the Aufbau principle and Hund's rule. The 2s is completely filled. The 2p has the three parallel spins that we would expect. Now, because it's 2s and 2p, the one that we pick should be in the second row of the periodic table. Remember, the rows of the periodic table tell you what value of n are. We have 2s and 2p, so we want to find something that's in the second row. So choice B, phosphorus, that's in the third row of the periodic table, and then arsenic is even below that. So choice B and D we can eliminate right away, because those are in the third and fourth rows of the periodic table. We're looking for something in the second row. Now, if we look at the other two, boron and nitrogen are the other two choices. All right, for 2s2, 2p3, let's pull up our periodic table. I need to find it. It's on my desktop somewhere. All right, so here's our trusty UH periodic table. If we look at boron, it's 2s2, 2p1. It's the first element in the 2p subshell. So boron would only have one p electron. What we're given here has 3p electrons, so we can eliminate that one as well. Now if we go to choice B, 2s2, 2p3. So helium are the core electrons, because what comes before 2s is 1s. We have 1s2, which is the configuration of helium as our core electrons. So that part is fine. 2s2, 2p3, that should be nitrogen. If we go back to the periodic table, nitrogen is 1, 2, 3 in the 2p block. It's the third element. So that's the correct configuration for nitrogen. But then if we look at the group numbers, 7a, 17. So these are, there's a little bit of confusion here. These are the two different conventions for group numbers. It's telling us the same thing. It's just giving us the two different formats for that number. So is it group 7a? If we go to this periodic table, these are labeled with Roman numerals, but nitrogen is in group 5a. So 7A would be the halogen group over here, which could also be labeled as 17. That's the number in parentheses that you're given. And the halogen group is group 7A, not group 5A. So this one has the wrong group number. So this is the wrong group number for nitrogen. The P3 or any column, any element in the P3, it should be group 5A. So we have the wrong group number here. It should be 5A. In an alternative format for that would be 15. So those Roman numerals, the Arabic numerals 1 through 18 are not given on your periodic table. We're given Roman numerals, and again they have 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and then the transition metals are labeled with B's. So there's two different numbering formats, and when we give you these answer choices, we give you both of them. What's called the IUPAC convention, the one that we give just simple numbers to, that's in parentheses. So these are just telling you the group number in two different ways, so don't be confused by that. But this has the wrong group number, which means choice C cannot also be correct, so the answer for this one is none of these. It's easy to doubt yourself and think that, one of these four choices must be correct, so maybe that was part of the reason for having trouble with this one, but in this case, all of these answer choices had at least one thing wrong with them. So choice C was very close to correct, and very many of you picked that, but in choice C, the group number was not correct. All right, finally, the last one I want to go over is ionization energy. So choose the element with the highest first ionization energy. Now, we know from class that if we're talking about increasing ionization energy, the periodic trend for this is as we go up and to the right. Now, this is not a perfectly smooth trend, though, and there are some exceptions to this. So the two main exceptions we want to be aware of for ionization energy. All right, this doesn't apply to all the periodic trends, just ionization energy. So group 3A, which we could also abbreviate as group, would that be 13? This is also 11. Group 3A or 13. Sorry about that. All right, those are typically going to have smaller ionization energies than group 2A, which would also be considered group 2 of the numbering system. So group 3A is to the right of group 2A, but it has a smaller ionization energy because these are NS2, NP1. Group 2A is NS2. So having filled subshells is a desirable situation, which means that group 2A, which has a filled subshell, would be something that is favorable, so that's going to have a higher ionization energy, whereas group 3A, if you lose the 1p electron, you get to a filled subshell. Now, the other exceptions we want to be aware of is that group 6A, which could also be group 16, is smaller than group 5A or group 15. Alright, so group 6A is the oxygen group, which has an NS2 NP4, and this is NS2 NP3 configuration for group 5A. And it's actually, in this case, it's not that, so group 5A is anomalously high because of the half-filled subshell. Alright, because again, we have a half-filled subshell for S2P3, so that's a favorable situation, and it wants to maintain that, so it doesn't want to lose an electron. Remember that ionization energy refers to losing an electron. Okay, so with that information in mind, we can go back to the question. We want to choose that with the highest first ionization energy, and we gave you the hint also to be aware of the discontinuities. Alright, so this is group 1A, group 2A, 3A, also 1A and 2A. So we're looking for the highest one, so we want one that's highest in the periodic table. So this is, this is below the rest, this is below the rest. But if we're comparing sodium, magnesium, and aluminum, those three are all right in a row. This is atomic number 11, 12, and 13. And again, we would normally expect it to increase right to left, but magnesium is anomalously high or aluminum is anomalously low, however you want to think about it. So a lot of you picked choice C, which is aluminum, but remember that this is group 3A, which is NS2 NP1, which has a lower than expected ionization energy. It doesn't follow that perfect trend. So magnesium is the one we want to pick. Alright, so there's just two exceptions we want to be aware of, and if you're comparing group 2A to 3A, group 2A is higher even though it's to the left, and the same goes for 5A and 6A. So be aware of those two exceptions, and that'll help you answer these types of questions as well. All right, that about wraps this up. As always, you're welcome to request topics to go over, and if there's anything that I didn't cover here that you would like me to rehash, either ask me in person or on Blackboard. Thanks.